Hello everyone, I'm Afruz and in this video I present our paper under the title Breaching the Two Approximation Barrier for Connectivity Augmentation, Reduction to Steiner Tree. This is a joint work with Jaroslav Birka and Fabrizio Grandoni. This work lies under the category of the survivable network design problems, in which the basic goal is to construct low-cost networks that provide connectivity guarantees between pre-specified sets of nodes even after the failure of a few nodes or edges. This indeed has many applications, but to mention one, I would like to draw your attention to the transportation system. Here, the cities and the roads are nodes and edges. Adding a new road has its own cost. Failure of edges here refer to roads getting blocked due to traffic jam or accidents. And the goal is to build a set of roads and add them to the current system, such that even after failure of some roads, still people are allowed to travel among certain destinations. We are interested in edge connectivity. Formally speaking, G is kh connected if for every subset of its edges of size less than k. If we remove this subset from the graph still remains connected. For example, here we have a 2-edge connected graph. Since the graph is connected, and if you remove any edge, the graph is still connected. However, this is not a 3-edge connected graph, since we have this subset of size 2, which you can see here, the red edges, that if you remove them, the graph becomes disconnected. In the connectivity augmentation problem, as an input, we are given a k-edge connected graph G and an additional set of edges, which we call them links. Here we have a 1-edge connected graph, a tree. You can see the tree has the black colored edges, and the links are the dashed red edges here. And the goal is to find the minimum size collection of the links such that if you add them to the original graph G, as a result, you would have a k plus 1-edge connected graph. An insightful theorem in this area is one by Dennis et al. It states that any instance of the connectivity augmentation problem can be reduced in polynomial time to k equal to 1 when k is odd and to k equal to 2 when k is even. So we can restrict our attention to the case where k is equal to 1, which can be further reduced to the case where the input is a tree, and we call this the tree augmentation problem or TAP, or to the case where k is equal to 2. Here it can also be reduced to the case where the input graph G is a cactus, and we call it the cactus augmentation problem. Note that the cactus is a connected graph in which every edge belongs to exactly one cycle. Here you can see an example of a cactus. You can see that in high-level view, you can interpret cactus as a tree joining the cycles. Let's review the previous works done in these areas. For TAP, we know that TAP is apex hard. Then there were a long sequence of improvements for TAPs in terms of approximation factor. The first algorithm proposed was a 2 approximation by Fredrickson and Yaya in 1981. Then the barrier of 2 was broken. It was later improved to 1.8 and then to 3.5. And the current best known algorithm is a 1.458 approximation by Grandoni et al. In 2018. For CAP, however, the situation is entirely different. As far as we know, the current best known is still the 2 approximation algorithm proposed by Kamal Jain. Another result in this area was our paper in 2019. Together with Galvez, Grandoni, and Sornat, we proposed a 3.5 plus epsilon approximation for the case where the cactus is a cycle. Here in this paper, we present a 1.91 approximation for the cactus augmentation problem, and we break the barrier of 2 for the first time. This implies that the problem of the connectivity augmentation problem also admits a 1.91 approximation. We begin by classifying the links into 2 groups. So consider this to be the original graph G. We have some links which the both endpoints belong to the same cycle. We call them internal links. The rest of the links, we call them external links. For the external links, you can see that in the high-level view of the cactus, there is this unique path from the first endpoint to the second endpoint joining is cycles, followed by this dummy internal link, which we call this set of dummy internal links the projection of this external link. Note that for internal links, the projection of the link is the link itself. We say that two links L1 and L2 cross if there is an edge L'1 in the projection of L1 and L'2 in the projection of L2 such that either L'1 and L'2 share a common endpoint. Like in this example, you can see that L1 and L2, they have this green link in the projection of L1 and green link in the projection of L2, and they share a common endpoint. So now we can say that L1 and L2 cross. Or if you consider L'1 to be UV, now L'1 and L'2 must belong to the same cycle, like here. And then in the cycle, if you consider the two paths from U to V, now the endpoints of L2 must belong to different UV paths. So here you can see that L2 and L1 cross because of the following property. Now consider the Steiner tree problem in which as an input we are given a graph G such that the set of vertices of G is partitioned into sets T and S known as terminals and Steiner nodes. And the goal is to find a tree with a minimum number of edges such that it contains all the terminals. We show that there is a reduction from the cactus augmentation problem to the Steiner tree problem. Consider an instance I of the cactus augmentation problem. Here the instance I is the graph above. Now for any link L in I, we introduce the Steiner node L in J. Here you can see that, for example, for the link L5, there is a node in gray L5 below. Also for any node T of degree 2 in I, we introduce a terminal node T in J. Here you can see that, for example, V5 is a node of degree 2. So here we introduce the terminal for V5. Note that in order to distinguish between the Steiner nodes and terminals, we use squares for terminals and circles for Steiner nodes. If there is a pair L and L prime such that these links cross in I, we introduce an edge between the Steiner node corresponding to L and a Steiner node corresponding to L prime. So here, for example, you can see that L5 and L2 cross, and we have this edge from L5 to L2. Now, consider any link if it's incident to the terminal T. We introduce an edge between the Steiner node corresponding to that link and the terminal corresponding to that node of degree 2. So for example, here you can see that L2 is incident to V5. So now we can see here that L2 is adjacent to V5 here. In the end, we obtain a polynomial time reduction from any instance I of the cactus augmentation problem to an instance J of Steiner tree problem with the set T of terminals such that any feasible solution of size alpha for I can be transformed in polynomial time to a feasible solution of size alpha plus size of T minus 1 for J. And also in the other direction, any feasible solution of size beta for J can be transformed in polynomial time to a feasible solution of size beta minus size of T plus 1 for I. Note that the reason that we have this small changing value is that in the Steiner tree problem, we want to minimize the number of edges. However, here we are interested to minimize the number of Steiner nodes in the tree since the Steiner nodes are the links. We also have a simple lower bound. So if you consider any feasible solution for the cactus augmentation problem, note that this must be an edge cover for the set of degree 2 nodes. The reason is that in the end, we want to obtain a 3-edge connected graph. So this implies that the size of opt is at least the size of T divided by 2. For instance, if you look at this example, you can see that V6 is not covered by the links. So if we remove these 2 edges incident to V6, the graph becomes disconnected. So this is not a feasible solution. Now we have all the ingredients needed to propose a warm-up algorithm for the cactus augmentation problem. Consider opt to be the optimal solution for the cactus augmentation problem instance. Now using the reduction, we can get a solution for the Steiner tree problem of this size. Then if you have any row approximation algorithm for the Steiner Tree problem, this leads to a solution of this cost for the calculus augmentation problem using the other direction of the reduction. Then using the lower bound that we proposed in the previous slide, one can obtain a 3-row minus 2 approximation. However, the current best known approximation ratio for the Steiner Tree problem is rho equal to ln of 4 plus epsilon. This is the result by Birka et al. In 2013, and unfortunately, this is not enough for us since 3 minus 2 is more than 2, and we are still not able to break the barrier of 2. However, to obtain a better approximation factor, what we do is that we basically open the box and we go through this paper and we try to modify the analysis such that we can achieve a better bound for our instance, which is a more restricted Steiner Tree instance. We recapture some parts from the analysis of the Birka et al. Paper. This starts by an optimal solution SC for the Steiner Tree instance I, rooted at some arbitrary node. Then they introduce a marking scheme in which for each internal Steiner node, they uniformly at random mark some child edge. So for example, here you can see that for L1, they mark the edge L1, L3. And they introduce the witness set for each edge, which is basically the set of pair of terminals T prime, such that the path from T to T prime contains that edge and has exactly one unmarked edge. So here, if you consider E, the pair V3, V9 is in the witness set of E, since the path from V9 to V3 contains E and it has exactly one unmarked edge. Then they show that they can obtain a solution of size sum over the edges, the expected value of edge of size of WE, where h of n is the harmonic number, or basically the sum over series 1 over I. For us, however, our instance is more structured than an arbitrary instance of a Steiner tree. For instance, we can show that there exists an optimal solution such that the set of leaves are exactly the set of terminals. Also, for us, we know that each Steiner node is adjacent to at most two terminals. So the idea is that we can focus on a specific marking scheme that can take more advantage of the structures of our instance. What we do is as follows. So again, we consider ST to be an optimal Steiner tree. Then we set an arbitrary node R as the root, which is adjacent to at least one terminal. For example, here you can see that we set L4 as a root, and L4 has two terminal children. Then for any Steiner node L, if L has no terminal child, then uniformly at random we mark one of the child edges of L. So here for L1, we either mark L1, L3 or L1, L2. And for the rest of the nodes, we uniformly at random mark one of the edges going from L to a terminal child. So here, for example, for L4, we mark the edge L1, V3. Note that L4, L1 is not an option for us. Then we have this lemma in which we show that for a Steiner node L, if you consider ML to be the child edge of L that is marked, and consider CL, basically the cost of L, to be the value, the expected value of H of size of WM of L, then we show that our approximation factor for the calculus augmentation problem is almost equal to the average cost of the links. The proof of this fact is not that complicated here. We omit the proof, but it suffices to note that this proof follows from the fact that basically the size of W is 1 if E is unmarked. Then using some algebraic manipulation, one can get this bound. Again, it's worth mentioning that this shows that now we can view APX as the average cost of the links. Now we categorize the Steiner nodes. The first category is Steiner nodes in which they have at least one terminal child. We call them good father. For example, here L4 has two terminal children, so we call L4 a good father. Then for a good father L, we call each Steiner child L prime of L good. So for example, here L1 is a child of L4, so we call L1 good. The reason we call these nodes good is that for these nodes and also for the roots, we have this property that the cost of these nodes is at most h of dl, where dl is the number of children of that node. This is pretty good for us since h of dl for our purposes is reasonably small. The other category of nodes are the bad father nodes. For example, here L1 is a bad father since it has no terminal child. For a bad father L, we call each Steiner child L prime of L bad. So here L1 is a bad father. So now L2 and L3 become bad nodes. For a bad node, bad nodes, however, the cost of that node is upper bounded by h hat of d of that node, where h hat of n is this value which we define here. This value is more than h of n, so basically these nodes, they have high cost for us. We show that in order to obtain an upper bound, it suffices to consider the trees that have the following properties. The first property is that every good father must have two terminal children. Here you can see that the color nodes are the set of good father nodes, and they have exactly two terminal children. The second property is that every bad father must have at least two Steiner children. Here you can see that the red node is a bad father and it has at least two Steiner children. We say that the Steiner node L is a leaf Steiner node if it has no Steiner child. So you can see here that the yellow nodes here are the set of leaf Steiner nodes. So here you can see that they have exactly two terminal children by the properties above. And the important thing to know about the leaf Steiner node is that their cost is either H2 if they are good, or at most H hat of 2 if they're bad, which in the end, in both cases, is a very small value for us. We partition the Steiner nodes into groups. This is done in a way that average cost per node in each group is small. So consider this example here. The nodes which have same color, they belong to the same group. The intuition of how this is possible to do that such that the average cost per node in each group is small is as follows. So basically, recall that leaf Steiner nodes, they have a small cost. So in each group, we try to put at most one non-leaf Steiner node. And if that non-leaf Steiner node has high cost, then we try to put more leaf Steiner nodes in that group, so this balances the costs. Another modification we make in order to balance the cost is that every good Steiner node L pays a present of small value to its father to balance its cost. Recall that good nodes have low costs, so this process helps to distribute the cost in a more balanced way. Note that the average cost of the nodes is less than the maximum of the average cost over group. Finally, we show that for this certain value of P, the average cost of each group is less than 1.91. So basically, this shows that our algorithm is a 1.91 approximation. Now the open problem. First thing that comes to mind is that can one obtain an approximation algorithm for the cactus augmentation problem of factor 3½ plus epsilon, same as what we did for the cycle augmentation problem? Or can we even do better, same as what they did for TAP? Another interesting approach would be is it possible to find a lower bound in terms of approximation factor for the cactus augmentation problem, which is significantly higher than 1? Finally, consider a variant of this problem in which the links have weight, and instead of finding a subset with the minimum cardinality, here we are interested to find a set of links with the minimum total cost. Now, for this problem, which we called it the weighted cactus augmentation problem, is it possible to come up with an approximation algorithm of factor less than 2? Note that this must be difficult since The well-known problem of the weighted tree augmentation problem is a special case of this problem, and the weighted tap has been standing on the barrier of 2 for a long time. This was all. Thanks for watching this video.